Hello everyone, we're going to be learning dynamic programming today, and it is one of my favorite topics. So let's get started with it. First of all, to get you a gist of it, dynamic programming is basically a technique in which you have a hard problem and you divide the big problem into smaller subproblems and you solve them and use the solution to get the result, right? A very simple overview of it. And well, how you say, well, we'll look at it going on with an example, okay? Now we are going to look at a classic problem, which is the knapsack problem, in which this is you. Okay, you are a robber who entered a house, and you're greeted with all these items. Okay, these are the items in the house. You have a bag on or a knapsack which has a capacity of 4 pounds. Now, well, of course, you as a thief would want to steal all of these items, but you can't because the total weight of these items is 8 pounds. So you think to yourself, you want to maximize the profit. How would you go about it? Okay, so like a very naive way of looking at it, which you are not, of course, but what a naive person would do to think of how to maximize profit would be look at all possible scenarios. One of the scenarios in his head would be, let's say, an empty knapsack, right? I mean, it is a possible scenario, right? One possible scenario would be only stealing the guitar. Another would be only stealing the stereo. And let's say another would be only stealing the laptop, right? Let's say he makes two combinations with this. He makes another combination, and well, let's say all of them. Okay, and well, that is of course a very brute way of going for it. For three items, it will take you like eight combinations or two raised to by three combinations. If you add another item, for four items, it will take you 16, that is two raised to by four. For five, similarly, it would be 32, and for n, it would be 2 raised to the power n. That is, it grows exponentially with the value of the number of items, right? I mean, this is a very bad complexity, right? If you look at it from the perspective of a programmer, if you solve a problem with n items in two raised to the power n time, well, it's just bad. Okay. Now, as we as programmers, it is our job to sort of think about the time complexity of a problem and how we can do it in less, right? So, first of all, let's look at it from the perspective of dynamic programming. So what we would do is we break it into small subproblems of the sort, like let's say maybe the knapsack was only of size one, like had only the capacity of 1 pound, or let's say only 2 pounds, or let's say only 3 pounds, or let's say only 4 pounds. Okay, or maybe we only had the guitar. Okay, or we only had the stereo. Okay, or we only had the laptop. Okay. Now, if we look at it like this, we sort of get this. Let's say we store these values for these instances. Okay. So first of all, we know that guitar takes one space and has a value of 1500. Okay. And stereo takes four spaces, has a value of 3000. And laptop takes three spaces and has a value of 2000. Okay. Now, simply put, let's look at a small sub-problem first. That is, we only have 1 pound bag, only one guitar in the house, and this is our smallest problem right now. Okay, so it is very simple. We only take the guitar and we fill the space. Okay, now looking at another problem, we have 2 pound bag and only the guitar in the house. We can only take the guitar. Similar with this and similar with this. Okay, since we only have the guitar, we can only fill the spaces with guitars. Now we look at another sub-problem, that is we only have uh, the stereo and we have stereo and guitar and only the 1 pound bag. So we have two choices. Either we take the stereo, which we can't since it takes four spaces, or we just simply go with the previous value, that which the one which we had with the guitar, right? So we get 1500 and a guitar. For 2 pounds, similar situation, 1500 and a guitar. 3 pounds, similar situation, 1500 and a guitar. Now, for 4 pounds, we are presented like since now we have the capacity of four, right? We can look at stereo. Now we have the problem here is whether we choose the guitar for 1500, which gives us a value of $1500, or we choose the stereo, which gives us a value of 3000. Well, the choice is very simple, right? Of course, this. So, um, yeah, simply this is 3000 for the stereo, right? And now for the laptop, it would be like, yeah, looking at the smaller subproblem, this one, we take for one space, since laptop takes three, we simply get the previous one, 1500 with the guitar. For 2 pounds, same 1500 for the guitar, and for 3 pounds. Now, here we are presented with a choice. Either we take the laptop or simply follow the previous choice. Now, simply we get, no, we, of course, we take the laptop and we get a value of 2000 and with the laptop. Okay. Now, for the 4 pound, this is interesting. Okay. Here we have two choices. One of them being either we take the previous choice, that is 3000 for the stereo, which takes us to a space of 4, or we take the laptop, that is 2000. Okay, and after laptop we have one storage space left, storage space of 1 pound. Okay, and as we can see, now we have to look at it like this. For every box or every small subproblem we are solving, we are calculating the maximum value that can fit in a knapsack of the given size in the limitation of the number of items. So we know that for a 3 pound bag with only the guitar and the stereo, the maximum item we can get in the bag is 15 of value 1500. That is a guitar, right? So similarly, in this we calculate, right, that we can get the laptop in. Simply we can either get the previous value or the laptop plus something in the remaining, like three. Sorry, oh, wait, 4 minus 3. That is the storage space taken by the laptop. That is the remaining 1 pound space. And how can we get the maximum value for the 1 pound? That would be the maximum value of 1 pound that does not contain a laptop would be just before the laptop, and just for the 1 pound value we get this. So we simply get 2000 plus 1500 from the guitar, and the value we get is 3500 by adding these two for the guitar and the laptop. And that is the maximum value we can get in the knapsack, right? It is, see how we divide it into very small subproblems, and we get a new sort of value, right? The maximum possible value we can get out of the knapsack, right? I mean, for those of you who are looking at dynamic programming for the first time, this might be slightly overwhelming, but just bear with me, okay? As we go on with this, you'll slowly realize how dynamic programming works, and it just does not come instantly. You realize it with different problems. For me too, it took quite some time. So, to get a better understanding, let's add another item to the mix. Okay, let's add an iPhone. Okay, the iPhone, let's say, take one storage space and gives us a value of 2000. Okay, so here comes the iPhone. Another row to this. Okay, now the items till now that we have stored are those that sort of have the maximum possible value given the size limitations and the item limitations. Okay, so now we get iPhone. We have two choices for the iPhone. That is, either we go with the previous value for 1 pound bag, or check if we can fit iPhone in it. Of course, we can put iPhone in it. For one, we get a new maximum value that is 2000. We use iPhone for that. Okay. For two, now here comes an interesting part. For two, we can fit an iPhone. Plus, we have one more storage space left that we can get from here, the maximum possible in one that we can fit. So we get 3500 from iPhone and guitar. For three, since we have no other options, it goes similarly. Now for four, okay. Now for four, we can either simply go with the previous one, of course, as we talked about, or we can fit one iPhone plus another item. The another item being one that is maximum possible in 3 pounds. That is this one. Okay. So we simply use this. A total becomes 4000 with um, the laptop and the iPhone. At every point, we only had two choices to make. Now you'd say how this is more how is this simpler compared to our earlier approach? Well, in our earlier way, for the four items, we would have taken 16 instances, right? Or 2 raised to the 4, right? But for this, we only took 16. But look at it from a perspective for like let's say 5 items. For 5 items, we would have taken like 32, but in this case, we would only taken 20, and this number becomes smaller as we go on. Okay, so this is simply the way we go about dynamic programming. There is another way of looking at it. The one we discussed just now is basically called tabulation. Okay, and another way or method would later study is we studied tabulation just now and will later study memoization too. Okay, you don't have to concern yourself with it. Was just to give you a basic idea of how dynamic programming functions. And we'll later talk about how you can implement this into coding problems. First, we're gonna look at the code for this one, but the basic idea is basically this. At each instance, you make two choices. Either you pick the current item plus the maximum value you can get in the remaining space. Okay, in the remaining space, or you don't pick the item and you just go for the previous max at that storage space. Okay, this is the basic idea, and you can see we have done it throughout this. We have like here we have just taken the previous values, but at points we have changed up those things. Okay, so you'll get a clearer picture once we do more problems and we look at the solution of this problem. Uh, the one thing I'll say to beginners is just stay patient. This takes some time to get used to and understand things. Just take it slow. Don't rush ever. You'll get it slowly. Okay. Now we're going to be looking at the solution. This is in C++, by the way, but the language does not matter. We are not going to go line by line for the solution. You can do it in the language of your choosing. The logic remains. So first of all, we're basically this I here is iterating through the items, and J is iterating through weights. Okay. So here this J is going through this and I is going through this. Okay, this is general idea, but what we are doing here is what matters. For every position of I and J, we are picking whether we are gonna take the item that we are currently on. Okay, for pick we're gonna take the item we are on and the maximum possible we can get before that, and or we're not gonna do that and we are picking the maximum. That is the basic idea, and at the end we are returning the final value. As in this, we got this result, so we are just returning this. This is just an overview of the solution. I want you to do this yourself. This is just to understand this, and if someone is struggling with this, it is no problem. It'll just take some time and you'll get used to it. And in the following videos, we're going to talk about how we come up with this equation. Okay, and some of you might have heard about how this is the tabulation approach and there is different memorization approach. At core, they are both basically the same. It is just different way of implementing it. We are going to talk about that too. But for now, this is the basic idea behind dynamic programming. I'll include the links and as well as my solution, these notes, everything in the description. And I wish you all the best in your journey and keep learning.